Not right now. Oh, yeah, it's the problem. I have no idea what resolution my laptop thinks this thing has. Ah, better.
Yeah, sometimes you just gotta unplug it and plug it back in.
Yeah, it's called plug and play.
Yeah.
Okay, good afternoon. This is the Think to Think Research Group. I'm Carsten Brummann. This is Ari Caroline. And it's Thursday afternoon. So if you get the impression that we're behaving a little bit strangely, it's just because we are completely exhausted and are leaving this hotel at 4 o'clock tomorrow morning to go on to the next meeting. There is a much better Node Welt slide, which we failed to paste in here. So you can just go to IETF org IPR for details. But I think by this time of the meeting, you have seen that. So you handed out the pink sheets. We have note takers.
Yes.
Do we have a Jabber?
Hannes is logged in.
Hannes, have you managed to log in? So can somebody show Hannes the internet? Okay, so, well, yeah, there is a mailing list, as with any research group or working group. And most importantly, we put out a GitHub repository for each of our meetings. And the one for this meeting is T2TRG/2018-IETF 101. So we have a nice program assembled for today. So the chairs will quickly speak about the research group and the status. Then Michael Costa will report from the hackathon that we had on the weekend and from the Wishy effort that was underlying that. Then Jan Jungboom will talk about something that sooner or later we all will have to do, put some machine learning on our microcontrollers. And while he will not talk so much about how that is going to influence our work, I think we all can start imagining that. Then Sumya will talk about a project that extends the range of interoperability testing to semantic interoperability. So that will fit nicely to Michael's talk. And finally, we will have a talk, and I'm not going to try to say his name on a microphone, from someone with a Polish name, about secure computations in decentralized environments. So this was a talk that earlier version of which was at the MDSS DIFs workshop, and we thought was interesting enough for us to look at. And at the end, don't go away before the end, we will have a quick look at meeting planning. In this case, we will mostly look at the meeting we will have tomorrow with W3C and OCF. Okay, so just to remind people what the research group is about, who here is new to the research group, has not been to a previous meeting. Okay, so let me quickly say why we are here. We care about a true Internet of Things, which means an Internet where things, including low resource nodes with very little computational ability and power, can communicate among themselves and with the wider internet. We are looking at issues in this area, in particular when there are opportunities for IETF standardization, or I should add, for cooperation with other SDOs, with other standards developing organizations to make them happen. So we don't usually do radios here. We sometimes have to look at the radios if they behave strangely. I will have a slide on that in a minute. But we normally start at the IP adaptation layer and end in the hearts and minds of end users. So this is about the range we are trying to cover here. That includes security, because nothing in the IoT can work without security. So recently we have had a big focus on semantic and hypermedia interoperability, and we have had a couple of meetings under the name Wishy, one physical and several over the internet. We also have a number of drafts, and the most important one is the IoT security considerations draft, which just entered IRSG last call. We had a workshop at NDSS on decentralized IoT security and standards. I quickly report about that in a minute. We had an interesting side meeting. So essentially, you know all these sums about how many people fit into a phone box. Of course, these don't work anymore because there are no phone boxes anymore. So we just used a meeting room for the same thing and had a side meeting with 29 people in the room Waterloo, which is about the size of the screen. And finally, we worked with OCF. We are having something like every 6 months a physical meeting, and we had meetings in between, in particular this time to talk about security and the ACE activity. Okay, let me quickly say something about the NDSS DIS workshop. Of course, those of you who work in security know that NDSS is one of the leading security conferences. They usually have a couple of workshops associated with them, and this time we managed to land a workshop on decentralized IoT security and standards. This was about combining two views, one that you actually have to have standards to get IoT security, and the other that IoT security often will not be based on centralized approaches, but will require decentralized or non-centralized approaches. So we had 12 papers, which are still in the process of being published. So it will take until about mid-April until you can download them. These ranged from a security analysis of current IETF work to much more speculative ideas. And yes, we discussed blockchain. Yeah, one of the talks we actually have asked the author to come here because he's based in London and tell us about it. So that will be later in this meeting. So what are we going to do next? Tomorrow we will meet in Prague with OCF and W3C Web of Things. So OCF is the Open Connectivity Foundation, the organization that resulted from the merger of OIC, UPnP, and the All-Scene Alliance. And they are doing very interesting standardization work, and they are a heavy user of IETF technologies. So it's a good thing to talk to them, and we will talk in particular about requirements they have on our standards. So that is really important for us. We have in about a monthly cadence Wishy calls, where we try to move forward on the work that this workshop, which was in Prague, by the way, started. As I said, we have WebEx meetings with OCF. Maybe we will have further face-to-face meetings with OCF. So I personally will be at one of the next plug test events of OCF. So that's one organization we try to keep contact on. And what we should also do is plan what we will do in Montreal. Montreal is an interesting area. There are also interesting local people there that we may want to contact. We certainly will do more Wishy-related things there. There has been some discussion about distributed discovery, which would follow a little bit the theme that we had at this workshop, but this still has to be defined. The documents of the research group, we have been working on a document called State of the Art and Challenges for the IoT Security, better known as Security Considerations. Do you have a question? Go ahead.
Padhu from Nokia. So in terms of these joint meetings, it may be interesting also to have a joint call with joint sessions with OMA. We have July, we have a test fest in Seoul, which is done by TTA. It's an organization, test standardization organization in Korea. It may be interesting to showcase some of this and also participate in the lightweight M2M test fest there. That may be a suggestion.
That's definitely a good idea. Do you know which week that is on?
I think it is 17 to 23, if I'm not, my mind is not.
I think that's the IETF week.
No, that's the previous week. The previous week to IETF is where we are meeting in Seoul.
Okay.
So that's like Monday to Thursday, so that we are breaking on Friday so that people like Hannes can travel and hopefully meet.
Good planning, yeah, very nice. Okay. But yeah, OMA definitely is one of the organizations that we have been cooperating with at IETF. So for instance, one of the CoAP plug tests was hosted by OMA, which was really useful because in the process we learned much more about the lightweight M2M specification, which was pretty young at the time. So it certainly makes sense to deepen that. Okay, so back to the documents. We got very nice reviews, in particular from Jim Shard and Stephen Farrell. We got lots of discussion on the list, and we are now going into IRSG review. And this is always a good time for people to actually look at the document and see whether it covers their requirements and maybe even learn from it if we did our job well. So the other document that is nearing completion is called RESTful Design for IoT. So this essentially takes the well-known architectural style that is underlying the HTTP protocol and much of the web work, and explaining how to use this for Internet of Things applications, because there are some things that may just not be very intuitive here. So that is a document that is pretty far advanced. There is a pull request in review right now. We develop our documents based on Git technology, so we use something like pull requests or merge requests to process larger changes. And there is also an issue right now that we have to cover the new patch and fetch methods that are defined in RFC 8132, is that the right number? Those are not yet covered in the document. Okay, so
Laura on that?
Laura, do you want to say something?
Okay, so as Karsten said, we tried to fit 30-some people in a room dimension for about 10 or 12. Other than that, the meeting went very well. There is a draft about some of these issues, but the main idea is that when we put administratively independent IoT applications, so something I put in my apartment, something you deploy in your apartment, no administrative relationship between them. We lose packets because of radio interference, and that's not the IETF's problem. But what some recent research results suggest is that the protocols are inducing kind of timing behaviors, sensitivity to the loss of certain kinds of packets that exacerbate these problems, and we can get kind of severe performance degradation at the protocol level, and potentially that is something that we need to think about at this layer. Right now, there don't seem to be good tools, use simulators, test beds that help us evaluate these sort of multi-network scenarios where we have independent networks sharing the channel. And just some of the things we discussed. This just potentially a number of IETF protocols, anything that's touching these MAC layers, 6LoW, 6TiSCH. Some other things that came at the discussion, this is obviously somewhere on the IETF, IEEE border. Clearly the MAC has to do most of the work here, but at administratively independent networks, the MAC only has kind of limited abilities to isolate the networks in the link sense. So I think there are some roles for IETF protocols to try to understand the performance in this environment and potentially try to make some improvements. Some folks also raised various possibilities for active or explicit coordination via high-level protocols. So there is a draft, and I encourage people to be interested in this.
Thank you. Gabriel Montenegro. Yeah, I was wondering if you could elaborate a bit more on this research, because, for example, in Europe, the ISM bands require listen before talk. That's not required in the US and in some other places, but that's why 3GPP with coexistence problems in bands that are typically used by Wi-Fi assumes LBT and builds on top of that. So my question is this research that you're pointing at, does it assume LBT is in place or not? Or is it that even with LBT, you still have all these effects?
So basically what we are trying to do here is point out a problem. So there is some initial research, but the main conclusion from that is we need more research. So it's not yet trying to answer all the questions. So essentially we are building this transportation system for cars that work on an empty highway. But in reality, we have hundreds of SSIDs in apartment buildings and all kinds of gardening systems and whatever that see each other in the wild, which never have been tested for that. And yeah, some things are tested, but there are a lot of situations that are just very hard to test in today's test beds and so on. So the idea is to just look at the situation and find out what other research can we get started based on the fact that we are no longer in the phase where we have a single thing that has a couple of nodes around it, but we have independently administrated a network suddenly meeting in the wild.
Okay.
And there are surprises. So our research shows there are surprises. What other surprises are in store? We don't know. We don't have the research.
Yeah, my only suggestion would be to look at it from a practical point of view in many regulatory environments. It won't be completely blank. There are some rules already in place. So it would be good to know in those places.
There is a draft. Some of this is discussed in the draft. I think maybe since this wasn't a main topic for the meeting, Karsten, it's up to, I'm happy to take discussion. Karsten, if you want to move on to the main program, I'm happy to refer people to the draft and mailing list. Okay, like I said, okay.
Thanks. Juan Carlos Zúñiga, Sigfox. So yeah, just responding to Gabriel, because I guess you didn't have the opportunity to be in the discussion, but you're right. All those points were definitely part of the discussion. There's multiple regulatory domains. If we focus, let's say, on ISM bands, there's different rules on every country on how you operate on these ISM bands. Not all these protocols follow the same MAC, for instance. So here we talk about IEEE, that's just part of it. Some protocols may not be following the same. As long as they comply to the regulation, they are legal to operate in this country, but they may not be legal to operate in this other country. However, I think, at least the take that I had from the discussion is there's still some potential to share some knowledge at higher layers. And that's why there's a pointer there to the white spaces protocol that was the POS protocol that was defined before, where, yeah, I mean, through the internet, you can get some knowledge that could be useful for your area. And maybe these bands, these operators are using or either private networks, public networks, standardized protocols, or from different entities, but still there could be some interesting information, like, I don't know, to me it sounds like a level of noise in this region, something that doesn't touch on privacy necessarily, but some useful information that could help me operate better. You know, there probably, you know, you can do something in IP, at the IP level, and communicate networks that may or may not be connected to the internet. Maybe at the administrative level, not at the device level, but still, I think there's
design the
potential.
solutions today, but yeah, I think
You're
there's more
responding.
interesting things that you know. Elliot, do you have 30 seconds?
Yeah, just a little less. The first question is, where and how do you want to continue a conversation?
On the research group mailing list?
Okay. And the second question is, within that draft, is there a data collection methodology that's recommended to try and characterize the problem a little bit more?
So the document really kind of focuses on kind of laying out the challenges systematically. It points to a couple of research results, both mine and other people's. The main point in the document is that I recommend that the T2TRG or some other mechanism, we try to understand what we would like to have for some practices for evaluating how the IETF protocols, 6LoW, 6T, roll, perform in this environment. We need to have a better understanding. That's really what the document says.
I apologize for following up, but even before we make recommendations about protocols, right? I think the first step is we might make sense. I agree with you on the understanding. As part of getting the understanding, it would be useful to have some sort of data collection / analysis methodology so that we can better characterize the problem. And this is a good place to do that.
I think we're not even there yet. I'm not sure as a community we even know what we want to know.
Okay.
So we really have to finish this topic. We are
just
already 30 minutes.
1 second to
over
say,
time.
you really need to look, and I think you're already looking at LP1, and there you have like an 80, like in all the working group and the things that we're discussing there. That's a really place to do, and there are a lot of interesting topics there. So all thanks for this one.
This touches a lot of groups. Right now, it's at T2TRG. There may be some discussion where or whether that needs to go somewhere else, but I think not now because Karsten has a program.
Thank you, Laura. So yeah, you can expect to hear more about that in the future. So let's dive into the agenda after these first words. So next is Michael with a report from the Wishy and Hackathon activities.
Slides right there.
Right, we had so I'm going to report on the Wishy part of the thing-to-thing research group. Wishy is the workshop on IoT and semantic hypermedia interoperability. And we've actually had 8 calls since the IETF 101 because we've had a lot of activity in planning this, our participation in the hackathon. And we really covered a diverse set of topics around the semantics and hypermedia. I'm probably not going to try to read through everything here, but essentially we looked at sort of top to bottom. So what is the nature of abstract semantics? How do we want to describe things in a way that's protocol neutral? How do we do semantic annotation? How do we connect with RDF ontologies and other data sets that are around, like these third-party vocabularies? So, the QUDT, SOSA, SSN that are fairly hard to use, and how do we make them easier to use? How do we integrate semantic metadata into the system? Where does it go? And who uses it? How do they use it? this idea of a layered semantic stack. There may be different semantics at different layers in the stack at different protocol levels. We looked at basically how to work with other SDOs around semantic interoperability, and also some of the more mundane sounding stuff like data types of engineering units, which is still really part of the picture. So from top to bottom. So the goals for this one, and we're probably going to have a series of these, but the goals for this is the second hackathon, but this is the first hands-on where we brought hardware and tried to make it do things, bringing the diverse things together to interoperate. And we wanted to start focusing on, where you would start in an application workflow with doing discovery and semantic-based discovery and software adaptation to different data models and different protocols, and that's generally the theme. For this one, we had HTTP, COAP, and MQTT protocols involved. I'm not sure anyone used the MQTT, but we used COAP and HTTP. We started with really simple application scenarios like, can a signal input like a motion sensor turn a light on and off? Just for very, very basic orchestration. And the implementations that people brought were W3C Web of Things, which we'll talk more about. There was a Yang Komai, there was a Komai-based implementation, tried to interoperate. There was OMA Lightweight M2M, client and server. And there were some various ad hoc device APIs, protocols, just a basic REST API, like you might see from various connected devices that don't follow any particular standard, but they still use HTTP and they still have a REST-ish sort of API. So and we looked at connected home and automotive domains. And the idea was, how do we make them work together? What's the technology that we use? And we started using some of the stuff from the W3C Web of Things group, because a lot of the goals and objectives are very similar. So we brought that technology in, and we'll talk more about that. But what we ended up with were being able to generate thing descriptions, which is a sort of W3C Web of Things metadata format from lightweight M2M instances that we could find on a lightweight M2M server. We started integrating Komai with thing descriptions. So to show that you don't really have to have any particular kind of protocol, what's the range of protocols that can be connected to. We brought a thing directory and we stored thing descriptions in the thing directory. I'll show more about what that whole thing looked like. And then we had at the end, we had the Web of Things implementation communicating with these different device implementations and different protocols. So thing description was what we used as the metadata, common metadata format here. And it's basically a media type with RDF. It describes the abstract interactions with things, so, read the temperature, lock the door, this sort of thing. And it also binds those abstract interactions to concrete instances of things that implement those interactions. So, things like the data shape, payload structure, data types, and transfer layer instructions, like use this protocol scheme, use this method, use these options. And so the applications use abstract interactions to interact with things, so they're decoupled from the underlying implementation. So the idea is to have one application talking with many different protocols and really doesn't need to know what the underlying protocol is. So here's a little picture that illustrates this. Thing description has both semantic annotation, high-level information models, and capabilities like what do you want to do in an abstract sense, and protocol binding, sort of from the device-specific protocols, how do you do it? OCF, lightweight M2M, IPSO, ... These are all based on COAP, but they use COAP quite a bit differently. There's not an easy way to use them all in a single application without doing some adaptation. And so that's what we do with thing description, is that's pardon me. a format for adaptation between these different protocols. So thing directory is what we used in the hackathon as a central registry of these thing descriptions. So basically, each device or connected thing registers its thing description in the thing directory, and then applications can discover them and find them using semantic queries. And thing directory uses the same protocol as core resource directory. So it's the same sort of handshake protocol with uploading the thing and having to refresh it and being able to go in and do URI queries on it to find what you want to look for. So there was one or more. We basically used, I think, one thing directory, but there could be one or more. But these are the well-known entry points to the system. You go to the thing directory, find your thing descriptions, and that tells you everything you need to know about what that device does, what that thing does, and how to interact with it. So, there we go. So this is sort of a schematic of what sort of roles and services are available. And connected devices register with thing directory, and then applications, buttons are a little small. Applications discover them. After that, the application might interact directly with the connected thing, or it might be interacting through some intermediary like a proxy or a pub/sub broker. And if it was a pub/sub broker, there's some coordination here to register in thing directory the address of the pub/sub broker and how to communicate with it as opposed to the thing itself. And some of these, like my entries, for example, and some others, registered both. If an application is on the LAN, it can find and interact with the device directly. If the application is on the internet at large, it can find a proxy and interact there. And the thing description just had more than one entry point for doing that, one for the local LAN and one for reachable over the internet. So here's some examples sort of showing that the same format, how the Yang implementation worked. It fed its stuff to a thing directory, and then the Servian, which is where the application runs, can then access the device. Same thing with an HTTP device that might have some ad hoc protocol, but REST-ish. It registers the TD, and then the application can discover from the TD and interact with the device. What happened? Oh, okay.
Michael, could you
Same
get
thing.
back? Could
Yes.
you go back one slide and explain a little bit what the entities are? So, so the HTTP, the green box, is that the IoT device? The green box, is that the IoT device?
That could be the device, or that could be an agent on behalf of the device.
Okay, but which one? So I'm trying to make sense out of this. I understand that the thing directory is the directory that you previously explained. Which one corresponds now to the application, sort of like, and to the connected thing and the intermediaries on the next slide? So like here, so I see the directory, thing directory. Which one is now the client that wants to access some data from the IoT device? Is the ComI device, is that the IoT device, and the application is the W3C Web of Things Servient? Is that true?
Yes, yes.
And where's the proxy here?
Sorry?
And the proxy, it doesn't exist here.
So, well, sorry. This is acting as the proxy for the device. The Servient is essentially an application proxy for the device. So the Servient interprets the transfer layer instructions from the thing description that it got from the thing directory, and it uses those to access the device. So in the W3C Servient software, we already have the adaptation for the protocol for the transfer layer. So we use that as the application proxy. So
I think you have to update the slides to get them in line with the architecture picture, because there's one entity that apparently missing, and some errors may be missing as well, because in the previous slide, the IoT device registered itself at the directory directly. In this case, it doesn't. And there's no application,
So, Hannes, only one clarification here. In the case of the hackathon, the green box was, for example, just a file. So it was not necessarily even created by the device.
no, I'm
In the
saying,
in the case of,
get the slides in sync so that someone understands.
yes, that's definitely going to be helpful. But these slides are more showing the architecture on the hackathon, which is not fully the same as the, let's say, ideal architecture. But this is how the hackathon setup was made. And the green boxes in general are the new ones that were built for the hackathon purpose.
Here's a better picture to show a lot of these things. So, for example, here, the lightweight M2M device going through the lightweight M2M server, and this discovery adapter will discover things on the lightweight M2M server and register them with the thing directory. So that shows the whole loop. That wasn't shown on the other slides, unfortunately. So I take it a good point. Well, we should fix those up to maybe put something like this a little more up front. So in the same way for the HT, so here it shows the device isn't registering this. The device is doing lightweight M2M to the lightweight M2M server. It only needs to have these tiny short URIs and numeric identifiers and all of that. Then this piece goes in and expands them and knows how to create all of the semantic annotation based on its knowledge of, lightweight M2M number codes and ipso smart objects and what have you. And then the servient can say, oh, I'm looking for a temperature sensor and can find this, and then from the transfer layer instructions knows how to interact with the device. And the same thing for the HTTP and COMI devices, but we didn't show the whole loop of how. So the HTTP device was a Raspberry Pi. It can basically go directly and register its things with the thing directory. Also, we had some cloud services that had, we're running on a DigitalOcean instance that had enough, CPU and enough resources to be able to go and both expose the devices and create the semantic descriptors and register them. All right. So next steps, we're going to go. We want to go look at semantic annotation and discovery like the thing directory case, but using core RD and link format. So how can we semantically annotate web links with the same information to enable the same sort of discovery on a general web linking format? We want to look at different end device protocols and data models. So, things like BACnet even are part of this, right? More automation of the semantic queries, because we're mapping the Sparkle endpoint to URIs. How do we make it easy to generate those?
Michael, when you did the mapping from, let's say, lightweight M2M to thing description from the W3C or other like COMI to that, how was that possible without losing some of the semantic or like? Because that has always been a challenge. Like we have all these different activities and we are piling on more and more standards activities on different descriptions, and then it becomes very difficult to map them to each other without losing some of the semantics of it. So what was that? What was the experience? Obviously you started with a simple scenario that presumably everyone has, but.
Well, when we're using these devices that are light bulbs and temperature sensors and stuff, there's not any semantic loss. In fact, the semantic annotations pretty much have a way of describing all of the what you want to do sort of things, and that's all extensible. So if you need more affordances, like what's the timing of changing the brightness of a light or things like that, those are all part of that and can be added. In the abstract, because we don't have to describe specific protocol features, it's sort of easier to cover the broad field semantically.
Right.
But a lot of the differences are in the protocols.
Yeah, but one of the challenge, or one of the observation that we learned from the IETF workshop was you can't just look at the data model, but you also have to look at the interaction model because they are closely coupled together somehow. And so it would be interesting to go from the basic example to something a little bit more sophisticated, like actuators, maybe other more complicated things, and see how well that works. I would be curious on what the result is.
Matthias Kovac, Siemens, to help out Michael a bit here. So there are different tracks going on. So in the W3C Web of Things, we look exactly at these interaction models that have partly describing what protocols are used, what are basically the abstract operations that you perform. There we found kind of this narrow base of properties, actions, and events that cover from a programming model perspective, basically what you can do. And so we can read out some state, we can write to some state if this is allowed in this particular ecosystem. We can call these actions that often correspond to something that goes on for a certain time. Some others might be RPC based, so there's also this coverage, and we can cover whenever a device can asynchronously send something to the client. So there we have this core model in the thing description, so there's a formal model behind the description document itself. And this is then extended a bit by the binding templates that Michael was mentioning. So in this example here, the common protocol was CoAP. So we are able to describe the methods that can be used by CoAP. We can describe if there are some specific options that are used for the protocol. And this is basically noted down uniformly in the thing description. So we can describe the differences there.
What I'm most interested in is reading up on some of that experience on when you did that. I understand, like, there are always some new standards efforts. I don't necessarily care about them. I want to learn, like, did those things that you tried to accomplish actually work out? Like, where are the problems? And maybe you've created those descriptions already.
Yeah, so for the descriptions, a big part of what I could explain until now is documented in the W3C document. So there are the drafts out there.
I'm sure the W3C document will not explain your experience with the hackathon on mapping lightweight M2M to the thing description. Right.
Okay, this part explicitly about that would be probably a report from this hackathon, which was just the last weekend, and I don't know how much time you had. But definitely this is something we are also working on. So there is another Plugfest happening at the W3C face-to-face the upcoming weekend, where also, again, people from different organizations come. There will be some reporting on that. And the last thing I just wanted to add, because you asked about the semantic level, so this is something that goes on top, and that is something that we're currently collecting. So it's looking into, okay, what kind of semantic interactions do we have in the different ecosystems, and actually listing this down and creating vocabulary. But there we need basically a good overview of what is out there. Maybe an activity to point to is the IoTschema.org, where kind of the ones that are easy to identify because they occur across all these ecosystems are being collected, again, in some kind of uniform format that can apply over these different ecosystems.
So, Ari Keranen from the floor. So quickly comment on the lightweight M2M experience. It was very simple thing that we did so far. So for sure, we're going to be learning more on how well the semantics map. So right now, what the prototype did is that it queries from the management server what kind of devices are registered there, what are the URIs that are exposed, and maps them to thing description. What will be the next steps is to do the semantic mapping and then figure out, like, how much tools, how much vocabulary do we have to get how close we can get the semantics. But it's a journey, so we'll keep you posted.
So these look like really good next steps. I really appreciate where you're going, but before you get to the more complex devices, I think it might be useful also to expand out your experiments with a more complex model of the existing devices. That is to say, Hannes's work with ACE and other things. So one of the challenges that when I talk to my partners in all this, by the way, I'm Elliot, I work at Cisco. The moment we add in an authorization model, it gets, even with the simplest devices, it gets pretty complex. And I think that's a great area for discovery. I realize I'm saying this without saying I'm going to do it, okay? But it's just we're going through this now for very simple cases, and they're turning very complex. Even trying to get something to market is very hard.
So that's a really good point, and what we're working on in W3C and probably need to look at here also, we're looking at how do we create security models for individual endpoints so you can authorize and learn how to securely communicate with them. And we're sort of seeing that as a next step, but not far behind. So, you know, are you using access control entries? How do you generate the correct token, subject, role for RBAC? You know, all of those things, we're trying to work that into the next phase of design for that.
Mason Lindine here in University of Essex. I'm wondering how big is the resource directory, the thing directory in here? Are you looking at the state? What sort of scale are we talking in here? Is it like a local network of things? Are you talking something a bit bigger? What's the size in here?
Well, I think a thing directory would be like a scalable web service or a thing that you would have on your router on your LAN, just like a resource directory.
So is that going to interact remotely? Is that going to interact remotely with other thing directories? What sort of scale are we looking at here?
Yeah, federation of thing directories we haven't really tried to work with, but there should be a way to create scalable services that provide this.
Right.
Either through microservices or through some federation of multiple instances of directories.
So what's the sort of discovery protocol are we looking at? Is it something innovative, or are you looking at some of existing protocols?
Sparkle endpoint.
Sparkle, okay, thank you.
Okay, so basically that's all really been covered. The one thing I wanted to say that we find we're looking at more diverse models. We're looking at an automotive model. And the automotive model is very dependent on being able to understand the feature of interest that a thing is bound to. So if I have a door switch, the automotive model really requires us to say which door that is and that it's a door. And that's something that we don't have in the IoT schema on definition model yet, but that's, again, the next thing we want to add is features of interest. And that basically creates a whole discovery system. What do I want to do? Which thing do I want to affect? And then how do I do it? I think I'm out of time. So.
Yeah, thank you. So as I said, this activity is going on. So this was just an intermediate status report. And now for something completely different.
Keep turn the screen a little bit so you can see the time and notes and stuff.
Yes.
Hello. Yeah, so indeed something completely different. I'm going to talk about a research project that is being developed in my team right now that allows us to do deep learning on microcontrollers, which I think is one of the most exciting projects that we can be doing right now. My name is Jan Jungboom. I am developer evangelist at ARM. And one of the first times that I was running into deep learning in the field was about a year ago. And that was here in the University of Technology in Arusha, Tanzania. And in there I was teaching at a summer school where a bunch of data scientists, mostly mathematics, master students and PhDs, got together to look at the problems that they had within their society and how they could apply deep learning or machine learning to these problems. And I went there as the IoT guy. So actually we went to the field. So the conference was 6 days. So during that time we did IoT training, like how do you build devices, where do you store the data, what do you do with it, and after we actually went into the field. So we went to dairy farms, we went to chicken farms, actually capturing data that then was published as an open data set that a variety of universities then used. So a university in Kenya was actually using the samples that we generated during that workshop. And I'm returning in May, very happy about it, called Data Science Africa. We're going to do 8 days, 100 students, 3 fieldwork projects, and again, just actually building something and getting this technology in the hand of students, and that's very cool. Now, if I think about machine learning, what I think about is large sets, large data centers, full of clusters of GPUs doing my training and crunching Facebook posts to resell them to Cambridge Analytics guys. But if we're taking one step back, actually a lot of the value of machine learning is added if we can run all these algorithms not in a big data center, but rather on very small edge nodes. So one of the cool projects that we've seen in the last year is sensor fusion, where you combine a number of relatively cheap sensors and get data points from all of those sensors. And on sich, these points are not worth that much, so you can't infer much from it. But if you combine a lot of cheap sensors together, you create like this, what the guys at Jira called a super sensor. So there's a really good video on that link, the slides will be published after this, where all kinds of stuff that happens in the house, like stuff like a faucet turns on, they can detect from this very, very small group of sensors. And that's all just because of training on a variety of different sensors at the same time in the school. Another thing is what happens, what Google is doing with their keyboards on Android, a technique called federated learning. Now, there's a local model running on the Android phones that gets locally trained as well. But what you don't want to do is send raw training data, because preferably if I'm a keyboard manufacturer, I want to get data from all my users and get that back and refine my global model that I then push out to all the Android phones. But I don't want to push any raw data into the cloud because there might be all kinds of privacy aspects in there. Plus, if I'm looking at how often I type, it costs quite a bit of bandwidth to just stream that upwards. So what Google is doing is they have a local model, they keep refining that, and they're sending them the changes in the weights in the model back to the cloud, and they use that from all the people to refine their global model. So it's this hybrid model where you do some training locally, and then take the learnings that you do in that model and push it upwards and update your global model that runs somewhere on a cluster of GPUs. Another thing is, for a bunch of file formats, we're really good at compression. If I draw a number or I draw a letter, then I don't need to send the whole image. I can just say, okay, well, that's an A, and I just send one byte over the line. But if we're going to look at larger data sets or interesting stuff that happens all around us, then I don't have a model that can compress the data straight away. So this thing called autoencoding, where you basically have a deep learning model that's going to keep producing features up until the moment that it has its own compression format, and you have the model on the other side where it can decompress that and basically give you a learned representation of what you try to send it. This is a model where the deep learning model itself is going to figure out an encoding scheme for this, creating very, very interesting compression schemes that we didn't devise before for very localized sets of data. This is very important if you look at low power wide area networks like Sigfox, like LoRa, where your uplink capacity is very limited. And sending a compressed version of whatever you're trying to send, even though it's a very complex problem, is worth a lot. And then the last thing here, so this is a photo from the work week that we did last year in Tanzania. It's like offline self-contained systems. What if you want to do something in an area where there is no internet? If I'm going to deploy a machine learning model on a dairy farm somewhere in Tanzania where the average income is under $100 a month and there's no internet, I'm not going to put down a cluster of GPUs to actually do some deep learning models there. But I am very interested in what machine learning can bring to me. So one of the things that we wanted to detect is, can we see if a cow is in heat at any point based on data that we get straight from the cow's skin? And that's important for the farmers because a semen sample is about $2 to $4. And $2 to $4 is a lot of money, so you only want to put that in if you have the highest chance the cow is actually getting pregnant. There's a little blog post about that there, it's pretty interesting. The other thing is there's some research, and it depends a little bit on what you try to do, what kind of inferencing you want to do, where doing it on the edge is actually a lot faster because you don't need to hold a round trip to the clouds, and especially if you think about LPWANs, might be even harder, where actually the energy per inference is lower on edge versus cloud. So this was Nan Wang, she was doing her PhD internship at ARM, and she was looking at some inferencing numbers, and this was for a very simple environmental monitoring system, where she actually found that the energy per inference, while doing it on the edge, even though it takes relatively longer and more cycles, was over 10 times more efficient. For other stuff like image recognition or video or object recognition in videos might be the other way around. But there are use cases where doing it on the edge is just more efficient. Now, if we have anything on the edge, it's not going to be a computer, it's not going to be a Raspberry Pi, it's going to be a microcontroller. So I assume everyone knows what a microcontroller is. Can I figure that? Well, I say, so they're small, they're cheap, and they're efficient. I mean, if they don't do anything, they just basically don't consume any memory either. But the downside, slow, and very limited memory. So that prompted us within ARM, or a couple of guys within ARM in our research, not in a complete research team, but a bit of the practical end, to come up with a library to do deep learning on these type of devices. Deep learning on microcontrollers. And that's the microtensor project. So microtensor is an open source library. It's Apache 2 licensed, specifically made to run TensorFlow models. So models that you normally train on your GPUs that you then run directly on a microcontroller. So it only does, at this point, classification, so no training. So what you do is you push a trained model that you train in TensorFlow down to the microcontroller, and after that you can do classification. With a couple of really smart tricks, we are able to do classification of a lot of machine learning models in under 256K of RAM. So that includes stuff like handwritten digit recognition, which I'll show in a video, but even object classification in videos. I think it's a really good step forward. I think it's really cool. This enables all kinds of incredibly interesting use cases without having to either upstream all your raw data to the cloud or do your inferencing on a really expensive machine. So it's developed, it's not an ARM project per se. It originated from ARM. These are the 4 core contributors. As you can see, I'm not there. Neil is actually in my team. He's the developer evangelist, Internet of Things for APAC. I helped the team a little bit, so I wrote the simulator for this, so it makes it a little bit easier to develop, but I'm not part of the core team. Also not a machine learningist, machine data scientist, anything. But it's very fun. If after this talk you're like, hey, shit, I want to develop on that, feel free. 4 people in the core team, of which none of them is their full-time job to actually develop this. We definitely welcome contributions. So just listen, get up. So here's a demonstration, and what we're going to do here is draw something on touchscreen, banana for scale. And after that, it will basically tell you what you just drawn on it. So I hope it's visible from the back because I was expecting a little bit larger screen. So this is a microcontroller. This 200 megahertz MCU. That's 3. Zoom in, and there's the 3. And this has a 300 something K RAM, and that includes the drive for the touchscreen. There's an 8. So this is a basic handwritten digit recognition running on a microcontroller in, well, less than 256K of RAM, which is cool. So what are we seeing here? It's essentially the hello world of machine learning. This is the MNIST data set, which consists of 60,000 images of handwritten digits. All these drawings are downscaled to 28 by 28 pixels, and then thrown through a deep learning model, where you do supervised learning, because with backpropagation, and the idea there is, in supervised learning, you try to map a set of inputs to their correct outputs, and because we already have the correct outputs for all those numbers, because they're tagged with the actual number that we expect, you use backpropagation to fix models in the model by actually working backwards. So this is trained in TensorFlow, just on a normal computer. The script is listed there, so you can run it yourself. And when we do the classification, because that is what we're doing in the microcontroller, not the training, we take whatever we just put in on the touchscreen, we rotate it so it's upwards, we remove the white space, and then we scale it down to 28 by 28 pixels, just as we have in the training set. And 28 by 28 pixels gives us 784 neurons. So every pixel is a neuron. So it's downscaled, black and white, 28 by 28, gives us a vector of 784 neurons. In the end, we get an output, so it's a single neuron. So that's what we need to work back with. We need to scale 784 neurons down to 1. Just before we have the output, we have an output layer, which is 10 potential outputs, because there are 10 numbers, 0 to 9, and then we run softmax on it, so we only pick the one that has the highest probability of actually matching. In there, then we run So what's kind of important is that what we do when we jump from the input layer to the hidden layer, so all of these neurons are connected on both the input layer and the hidden layer. Just before we do a matrix multiplication with a known set of data that we know from the training set, with a little bit of bias, which you also know because we trained this model, and then we run an activation function. We do that twice. We can talk about like the actual details of this later. Now, why is this important? Because how are we going to run this on a microcontroller? This looks hard. I thought this kid was cool. So what's important is this matrix multiplication table, because that is what that's kind of drives the memory usage of this model. So we have on the left side 784 input neurons, and you have a hidden layer of 128, and a hidden layer of 64, and then an output, well, actually a hidden layer of 10, and an output layer of 1. Holding it all in memory, that's what we want to reduce. Because for a lot of machine learning models during classification, RAM usage is the thing that just explodes. So the biggest trick that we're doing here is that we do quantization. And typically what you hold, the weight of the neurons is held in a 32-bit float. And that's completely necessary during training, because it's the only way you can properly hold everything, have like proper accuracy. We figured out, and the guys in TensorFlow figured this out as well, based on research by Pete Warden, is that if instead of 32-bit floats, you use 8-bit integers, you have a little bit of loss in accuracy. So tested against the Cypher10 dataset, which is a object classification in video feeds, about 0.4% accuracy loss. But that drastically reduces the amount of memory that we need, usually 4 times. So TensorFlow requires floating point dequantization. So if you quantize, you map a floating point to an int 8. So you hold the minimum value and the maximum value that you might have, and then you map it in between. TensorFlow requires to put it back to a float whenever you're done with a neuron. We worked around that because this is very slow on microcontrollers that doesn't have a floating point unit, which is a lot of them. So that's a way around it. And then we see the current memory usage. We're very aggressive at purging layers. So if we're going from the input layer to hidden layer 1, we don't load anything else in memory. So, and then you see that the matrix multiplication table that you need in the first hidden layer is dominating the RAM usage. So for this model, we see a peak memory usage of 98 kilobytes. And that is a lot less than 256K. And we can push this even down further with a couple of other tricks that we're doing. First of all, we have paging of memory for larger models. So if we see that we can't fit everything in memory because we have too many neurons at some point, or we have the matrix multiplication table doesn't fit, we can page through memory. Of course, sacrifice speed. So your classifications will go slower, but this is a way of even running these algorithms on microcontrollers that have less than 128K memory. We put the complete graph in ROM. So if you have a TensorFlow model, there's the graph, which basically describes all the layers and what to do with these layers and where you want to read the data from. We pre-compile this and put it in a read-only memory. So that saves a bunch of ROM, basically saves a bunch of RAM, in our case 26K. So that's great, actually. And something that we're looking into right now is that we want to take advantage of the sparsity of data. So that's going to cost a little bit of accuracy, but we might win a little bit of memory with that. Not all the operators are there. What's the most important ones that are missing right now are convolution and pooling, which are necessary for image recognition or object recognition in video files. And these these are work in process. And now the operators are important because these are the same operators as in TensorFlow. So the whole idea of microtensor is that we want to keep parity with what TensorFlow is doing. So we don't want to have a new way of training your data set, because all that happens currently in TensorFlow, and that's really cool. There's a lot of innovation there. Like there's startups now that are doing JavaScript machine learning, and they back everything by TensorFlow models. So we win a lot by doing that. So it's going pretty soon, convolution and pooling, and then we can also do image recognition. The tensors that we have right now, so in TensorFlow, everything is RAM-based, because often you run this on a machine that has enough RAM. A couple of ways of tricking that is that we also have flash tensors, where they can read from flash, of course, at the sacrifice of speed. The sparse tensors, and there's also network tensors, which I figured might be interesting here for people in IETF. So one of the things we can do there is say, well, we're going to split part of our data set between devices, and those devices might be in a mesh, and they can all work together to actually solve this, do this classification. I think it's cool. It's something it's a floating idea, it's nothing has been implemented, but it might be cool to have like 100 very small devices all working together to do a classification. Of course, only if your computation is costs more than actually the overhead that you have to send all the data around. So the workflow, microtensor consists of two tools, the CLI and the library. So you start with a set of data, you throw it to TensorFlow, that gives you a protobuf file. Then you run the uTensor CLI tools. That does two things. One, it creates the matrix multiplication tables from the trained model. So that's your trained model, essentially. And then it generates a C++ and an HPP file that contain the tensor graph. You combine it with the microtensorlib, and then you have something running on a microcontroller, and then you can put data in and get classified data out. If you look at, I don't know if you guys if anyone has used TensorFlow before, but you have TensorBoard, which can basically show you your current graph. Visually represented there, and then we just put it in code here on the right, and that's how we put the graph into run. Looking at time. Developing can be a lot easier. We have something called the simulator. It's developed in the same team, also in my team. So we have the same MNIST data set here, and we don't want to run it on a device because it's pretty slow, and if you want to refine the way that you do classification, it's a bit annoying as well. So we have an online simulator, just runs in the browser. 2, 3. And what it does is actually cross-compiles the complete model into JavaScript and then runs the complete inferencing in JavaScript. And it's a really nice way of doing your development. Something that's new that has just come out is a bunch of kernel extensions for Cortex-M. It's called the CMSysNN. This is developed by ARM, and the whole idea is that it leverages the DSP and SIMD functions in your silicon if you're using Cortex-M4, Cortex-M7, or Cortex-M33. And you use it to speed up a bunch of operations that you normally do, like, for example, convolution or ReLU. So we see a speed up about 4 to 5 times, which is pretty awesome, because stuff that you might think is kind of impossible, like object classification in an image, becomes viable this way. Because of this hardware acceleration. Microtensor doesn't use it right now, but it will do that very, very soon. So here's a video of a Cortex-M7 device running at, I think, 300 megahertz, more or less doing object recognition. So here in the left corner, you'll see the what it currently classifies. And in the right top corner, you'll see the data feed from a webcam. And then it gets downsampled to, I think, 32 by 32 pixels in the color image. So sees a frog now. Okay, I think this is pretty cool. So this is actually running a Cortex-M7 on a microcontroller doing live object classification in a video feed. It's pretty amazing. So the speed of this, it is measured on the Cortex-M7 running in 260 megahertz with 132 kilobytes of RAM used, still running under 256K. At this point, because we have enough RAM to keep this in, so the speed of the microcontroller is actually the limiting part. Having a Cortex-M4 or Cortex-M7 is definitely going to help you with use cases that require lots of computation. So here we have 3 convolution layers. So before CMSysNN, this took about half a second, and now with CMSysNN introduced, we can do this in 100 milliseconds. So reach 10 frames a second, analyzing a video feed on a microcontroller that is $2.50. I think is absolutely crazy. So recap, I'm holding a little bit short because we're also already over time. How to get started? Well, 1, buy development boards. I was told not to do any promotional activity because people in IETF don't like that, but we have a bunch of development boards that are compatible here. There's a link, clone uTensor, and profit in the end. So I think this is really cool. Like for me, when I ran into this, my other interests are LPWANs, you know, and sending large sets of data over the line is impossible. And this allows me to do actual intelligence on the edge, or actual intelligence in a home automation system where devices talk to each other, but where I don't actually have to push everything up to the cloud. And I think this is going to be shipped in a wide variety of products, and it definitely has a chance to push the Internet of Things into the hands of a lot more people. So with that, thank you.
Thank you, Jan. So we have time for about -1 questions, but if somebody feels a strong urge, one guy is coming up, or are you just leaving us? No?
Yeah, well, maybe it's more Edgar Ramos from Ericsson. It's more like a comment than a question. The problem I see with this kind of architecture is the same problem that we can see, for example, with mobile phones and having this kind of many, let's say, microcontrollers or equipment that have their own things, and then how you can actually address all of them. So let's say you have one algorithm that you want to put in any device, and then how you actually do it in such a way that you can port it to many places. So that's something we have to overcome somehow. And I think standardization might be one way to do it.
Yeah. Good. It was more a statement than a question. But yeah.
Exactly.
All right. Up next, I guess. Yeah, I'll be around. The slides are already online, janjongman.com. If you want to toy around with Microtensor or with the simulator, labs.emba.com, your browser, and go ahead. Thank you.
Thank you. So the next item on the agenda is a remote presentation, so we have to fiddle a little bit here.
So do we have? So Sumi has to take control.
So, Sumia, can you take control?
Let's see, how can I do that?
Yes, but he should be able to do that.
So Sumi,
I am connected. I'm trying to see if, presentation mode, no.
or perhaps someone in the Meeteco team can change that.
Do you know how can I do it? Because so far I don't see.
Okay, so if the remote presentation mode doesn't work, we can also show the slides from here and just have to say when you want to have the next slide.
Yeah, I think that would work.
Okay, go ahead.
Okay, good afternoon, everyone. First of all, my apologies because I couldn't be there for the presentation, so I have to do it remotely. My name is Soumya Datta. I'm a research engineer in Eurocom, located in the Sophia Antipolis in France. And in this presentation, I'm going to talk about testing semantic interoperability. It's a small industrial extension of a European Horizon 2020 project called FInterop. And for those who don't know about Eurocom, just in one slide, you already see it. So we are a graduate school and research center in digital science, and we have many academic, industrial, as well as institutional partners whose logos you see in the screen already. Next, please. Okay, so my presentation would be very brief because we have just started our work, and I'm basically reporting what we have identified as gap in semantic interoperability testing. What do we propose, the two ways, and I'm conducting a survey, and finally conclude the presentation. Next. Okay. So as you know, the Internet of Things not only requires smart infrastructure, but also deployment of new services capable of supporting multiple scalable and cross-domain applications. It is often identified and said that interoperability is the key to achieve the full potential of the IoT market. And due to the highly dynamic nature of the IoT, there is a strong need of interoperability at the data level. And in that case, it would be easier for aggregation, processing, managing, and storing data coming from all different IoT devices. So recently, many European as well as industrial projects, they have identified semantic interoperability as a way to address this problem. Next. So we need basically a way to test that would validate the semantic compliance and interoperability among different IoT systems. And this, in order, would boost the acceptance and adoption of semantic technologies by IoT market. And this is particularly important because when I talk to industry, a lot of people, they tell me that they understand the benefit semantics is bring to IoT, but they don't have a way to test and quantify those things. So that's why in this industrial extension projects, we identify testing semantic interoperability as a quite a gap in the current IoT research and industrial initiatives. And as mentioned, so within the scope of FInterop projects, in CENTEST, we are actually looking into how we can provide some tools, requirements, and guidelines for testing semantic interoperability. Next. Okay, so in CEMTest, we propose two types of testing. The first one being semantic conformance testing. Here, we want to test if a piece of semantic data conform to a reference ontology, any reference ontology, but it has to be a reference ontology. And in the second, the type, it's about interoperability testing. So it is to check if two parties or two system under tests understand correctly the exchange semantic data. Next. So initially, when we started working on it, we started gathering requirements for both the conformance test as well as the interoperability test. So for the conformance test, we basically clustered everything around three main checks. So we should first perform lexical check, then go into a lot of syntactical checks, and finally doing semantic checks. Next. So this is a very basic test scenario that you see. So we have one system under test and a tester. So the SUT basically sends a piece of semantic data to the tester, and it would, in sequence, would perform all the three checks, generate a validation report, and send the validation report back into SUT. Next. Then we came into semantic interoperability testing. So here, we feel that, again, three levels of validation is necessary. The first one being communication level check. So here, we basically want to see that the message sent from the first system should be received completely and correctly by second system. Then we have lexical or format level check. Here, the message issued from the first system should be in correct and understandable format for the second system for further data processing. And the third level is the data processing level check. Next. So I tried to represent a very basic scenario using two system under tests here. And in this particular test, our objective is to test the semantic processing results into, from the two systems. So consider SUT1, it sends a piece of semantic data, let's call it D1, to SUT2. And the SUT2 runs a query Q1, a Sparkle query Q1 on top of D1. And then SUT2 sends back the result R1 as well as the query Q1 to SUT1. And the system under test 1, it would execute the same query Q1 on the same data it had sent before. And let's say the result this time is R1 complement. So SUT1 would actually verify if both R1 and R1 complement are the same. So if they are same or equivalent, we'd say we have 100% interoperability. Otherwise, we'd say these two system under tests are not semantically interoperable. Next. Now, since Eurocom and our partner in the project, Easy Global Market, so we both work as well as follow the 1M2M standard. So we want to map the interactions and the system under test in the previous slide with 1M2M entities. So in this presentation, you see that we have clearly segmented. Ari, I'm getting quite some echo. Okay. So in this slide, you see that we have basically identified the application entity as well as common service entity of the 1M2M architecture, and we show the same set of operations, and we divide them with respect to the application entity and the common service entity. So it's basically the same representation of the slide 10 with respect to 1M2M in this slide 11. Next. Now, things starts to get a little bit more interesting when we introduce additional computational components between the system under tests. So let's say we have a query server which is generating the query Q1, and it is sending the same query both to SUT1 and 2. So, and then the system under test, they execute the query 1 on their semantic data and return the result to the query server. And the query server is going to compare R1 and R2 and check if they're same. If they're same, then we have achieved interoperability. Otherwise, we haven't. Next. So the next test we are doing is to see how to achieve interoperability at the data level. So in this particular case, so we extend what you saw in the last slide into this side. So we have two system under tests and a third-party tester. So so here our objective is to test the semantic data for checking if they share the same vocabulary. So when SUT1 sends the semantic data D1 to the tester, so the tester would retrieve the vocabulary V1 from the semantic data it receives. And it would do the same thing for D2 coming from SUT2. So it would retrieve the vocabulary V2 and then compare V1 and V2. And the comparison result would be sent to both of the system under test. And if we see that V1 and V2 are identical, then they're said to be interoperable completely. Otherwise, they're not interoperable. Next. Then we also can think of a little bit more complicated scenario for data level interoperability testing. And the main motivation of imagining or conceiving this type of scenario is that we have to, since we are building an industrial extension of the F-interop platform, so we would like to use what F-interop offers and extend it with respect to additional components. So the comparison server that you see in the center of the slide could be coming from all the already developed project, and in some tests we can think of bringing the SUT1, 2 as well as the two testers. And here the principles remain almost similar that you saw in the previous slide. So we retrieve the vocabulary V1 from the semantic data A1, and we retrieve the vocabulary V2 from the semantic data A2. And then the two testers are sending the two vocabularies V1 and V2 to the comparison server. Then the comparison server is evaluating them, and if both of them are same, we have 100% interoperability, otherwise not. Next. Okay, so that was all my presentation. So it was basically, I was telling you the first steps that we have took so far to define the different tests and the scenarios, architectures, different data that's going originating from one system under test 1 to 2, if we have additional components in between. Now we are also doing one survey. So I would request all of you to take about 5 minutes and complete this survey. Ari has already done it. And it's my request to all of you to do it. It's going to help this project a lot. And if you see I have missed any requirements or did not consider any requirement, feel free to drop a note there as well. Next. So in a nutshell, my presentation is about how can we test semantic interoperability, because it's highly necessary for different IoT systems. And in this project, we have proposed 2 types of tests, and we propose some scenarios to implement the semantic performance and interoperability tests. So I think I have a typo there. And as of future work, so we are actually implementing this test within the FInterop platform. So we are currently seeing how we can align the system under test with respect to what FInterop has as of now, and how we can integrate our the system under test as well as the tester and the software components into the FInterop platform. And we'll soon be reporting our results pretty soon. Next. So this is our acknowledgement, since SemTest is an industrial extension of the FInterop project, which I received funding from European Union H2020 project. And SemTest is a joint collaborative project between Easy Global Market and Eurocom. So we both are located very close to ETSI. If you have visited Sofia Antipolis, so you'd definitely know. That's all. If you have any question, you can ask me, or if you are coming to the Web of Things meeting, so we can meet and discuss personally. And please take the survey. So that's going to help a lot. So with that, I would say thank you very much for the opportunity to speak here, and thanks for your listening.
Thank you, Soumya, for doing this so quickly. So Soumya was here for the hackathon over the weekend, but had to go back. And for once, the remote presentation has worked reasonably well. So thank you. Do we have any questions? Again, we have time for about none, but okay. Thank you, Soumya, and we'll go on to the next presentation.
Okay. Thank you, Carsten. Bye-bye.
Bye-bye. Bring it up.
So just when I tell it, you just press enter.
Yes.
Sometimes it takes some time for them to be patient.
You're always patient.
Okay, thank you. So I'm Michał Król, I'm from UCL College London, and together with my colleagues, we currently do quite a lot of work about outsourcing computations. So when we want to outsource some computation, basically we have some requesting node which has some input and payment that is willing to pay for the computation, and then the executing node, enter. Yes. So we basically want to send the input, enter, then provide the result, send it back to the requesting node, enter, verify that the result is correct, and then in the end going to perform the payment, enter. Great, thank you. So right now this is done in the cloud. So we have Microsoft, Amazon, Google, they have the cloud, we have the computations. This is the cloud has its unlimited resources, and we get back the results. However, we have, I think here I don't have to convince anyone that running it at the end has several benefits in terms of delay, cost, and also in terms of privacy. So in our vision, we want to have a mesh at nodes. So even if I have my laptop, I have some spare CPU, I can just accept some tasks, run them locally, and be paid for the execution. However, it changes kind of the trust management, because because if you have Google or Amazon, we have to trust, give them our data, and you trust that they're not going to misbehave. Here, we have like untrusted nodes with laptops. The security and privacy must be built in the system design. So we cannot just trust that the other party is not going to misbehave. We have to be sure that it's not going to happen. Also, we want to have this open system when everyone can just join, so no vetting system. If I have some spare CPU, I just join and execute stuff. We want to have incentives, so the nodes are rewarded for their work. And we want this to be called centralized without any consent or judges that will act in case of conflict. So concerning the rewards, of course, if I have my laptop and I'm using my CPU to run computation for others, I want to be rewarded for that. So it should be also the main driving point for joining the system. Because in many peer-to-peer systems, that was the problem, there were no incentives. So if you consider torrents, everyone wants to get files, but then why would I use my bandwidth to give files to other people? However, before paying, I would like to verify the result. So be sure that I didn't receive just a random string of bytes. And there's also this problem when the payment should be done, because if I'm a requesting node, I don't want to pay in advance, because then the execution platform can just take the money and walk away. And the same applies from the execution node. So you don't want to run an execution before being paid, because then again, you send back the results, and the guy can just walk away without paying. So the result verification is also a very crucial part of the system. So we can have different types of tasks. So we can have proof of work types of tasks when it's very easy to check if the task was correct or not. So we just compare it against the hash. However, usually verification means that we have to recompute the whole task and then compare it, the result is the same. So in many systems, we can generate cryptographic proofs, like zero-knowledge proofs, to prove that the result is correct. However, usually it implies very high cost. Sometimes it's even much higher than the computation itself. And also, it's not available for every single computation. Another solution would be to send the task to many people. Then we get back the result, we compare them. If they're the same, there's a high chance that that the result is correct. However, it's highly inefficient because we have to pay for every single computation. And also we have to prevent colluding, because if two execution platforms collude, they can just send me the same random result. And then I have no idea that something bad happened. So then we also submit some input and we get some results, and we want to make it private, but not only private from the network, but also from the execution platform. And this is difficult because the execution platform must actually compute something on top of our data. So in the cloud, usually now we use homomorphic encryption. However, again, it introduces quite a lot of overhead, and it's not always possible. The other solution would be to use trusted execution environments, which basically allows us to write, to have trusted enclave on untrusted nodes. However, they require dedicated hardware. So now I just present a few key technologies we use in our system. So first is Intel SGX. So it's an example of this trusted execution environment. So basically what it does, it allows us to create a protected part of memory that is, and an enclave running on top of that. So then only this process can read and write to this part of memory. It is invisible and encrypted from the operating system or the hypervisor. And this Intel SGX comes with a remote attestation protocol. So if I'm a remote node, I can check, first of all, if on the remote host I have the valid Intel SGX platform, then I can verify that the function running on the remote host is the function I requested. And in the end, I can also establish a secure communication channel. So I can communicate directly with the function, kind of bypassing the execution node. And we also leverage heavily on blockchain. So we built on smart contracts that allow to add some logic on top of a blockchain. In our case, it's Ethereum with Solidity. So featuring complete language. However, everything that we submit to the blockchain is publicly visible, so we have to be very careful with this question. Chris.
Yeah, just a request to speak a little closer to the microphone.
Oh,
please.
okay, okay. Is it better? Okay, sorry. So then the problem with smart contracts is that, first of all, they're pretty expensive to execute, and second of all, there is quite a long delay, because if we submit a transaction, then we need to wait till it's confirmed. So to tackle up this problem, we also use payment channels. So payment channels allows us to run transactions off-chain, which is like much, it is like almost no cost and no delay in processing. So they're secured by deposits run on top of blockchain. However, all the communication is off blockchain. And the last component are oracles. So smart contracts by themselves, they have no knowledge or they cannot communicate with the external world. So we have like virtual machine, and oracles can act as trusted data feeds. So if I want to query a trusted HTTPS server, I can do it with an oracle, and then I can get also a proof that the data I got is valid. So then the overview of the system, just the assumptions. We have requesting node and executing node. They both distrust one another, however, they trust the function. So if I call this function, I know that it's gonna do image processing or video rendering. However, both requester and executing node, they trust the blockchain. And also we assume that the executing node has complete control over its system, operating system, hypervisor, and so on. There's gonna be a lot of so here, as previously, we have on the top we have requesting node that has some input. On the bottom we have the execution platform, and on the right we have blockchain running with smart contracts. So first of all, enter. The execution platform runs the enclave. Enter. Now the requesting node can establish this secure communication with the function. Enter. And verify its identity. So now Enclave can generate a proof, enter, and send it back to the requesting node, enter. Now we know that it's secure to send our input to the Enclave, and again, this input that we send is now secured from the executing platform. So it's only visible for the function, enter. So now, after some time, the enclave will compute a result, and at this point, the execution platform generates a secret, a key. So this key is then transferred to the enclave, and the enclave will use this key to encrypt the result, enter. So then this encrypted result is sent back to the execution node. So now we have the result, however, it's encrypted. Enter. We also send a hash of this key that we use to encrypt the result, enter. And both the result and hash have attestation from the enclave, so we are sure that they are correct. Enter. So now the execution node is sending a transaction with the payment for the executing node, executing platform. However, it can be unlocked only if we submit a secret, this secret key, and we can verify it using this hash, enter. So now if the executing node submits the secret to the blockchain, it will unlock the payment, enter. And at the same time, the key becomes visible, so the client gets the secret and can use it to unlock the result, enter. So here it works, however, we have two problems. So first of all, it can be pretty slow and expensive to do everything on the blockchain. And second of all, I can always send some computation to the executing node, wait until it executes my stuff, and then just walk away. So this kind of denial of service attack, enter. So to deal with this problem, we here introduce payment channels. So now sending this money and unlocking is cheap. It has almost no cost, and it's also very fast. So we can So we can divide our task into into a lot of small tasks and do everything chunk by chunk answer. So here the whole process is the same. However, because we don't require any cost for the transaction, okay, so we can do it very quickly. So now even if I submit a chunk of work, I don't know, 10 seconds of CPU and just walk away, the execution platform loses only 10 seconds of its time and not more. Enter. And to make it perfectly secure, the problem is in this communication. So in this channel of data between the requesting node and the enclave, because it's secured and no one knows what's happened. So if the communication fails, the smart contract or no one else is not able to say if it's because of the network failure or because the execution platform didn't want to compute anything, or maybe just the requester walked away. Enter. So basically, we can either submit everything to the blockchain and then everyone will know. But of course, it implies a big cost. And in our solution, we decided to go with IPFS. So the result, if there is a problem, so the requesting node just walked away, the execution platform has this ability to put the result on the IPFS. Then the smart contract can use Oracle to query it and verify the file and unlock the payment for the execution platform. That's all. So to conclude, we have a system for result verification and automatic payments. It is fully automated, and we have orders of magnitude lower overhead than the state of the art. We have no third parties involved. However, we have those limitations because it runs on Intel ATX, so it requires specified hardware. And currently, the limit of the application is up to 100 megabytes.
Is there time for a short question? I was wondering whether you did a comparison with some of the other sort of edge computing solutions that are out there.
Sorry, say again?
Did you do a sort of a comparison between your approach and some other edge computing platforms out there? Like there's, as you know, there's work on OpenFork, like Microsoft, Amazon, and others have sort of an edge computing solution. And so I was wondering whether you've done a comparison.
No, it is fairly early work, but I'm not aware of any solution that can prove you that the result is correct.
Well, obviously they have different characteristics, but there are pros and cons. So that would be interesting.
Yeah, we started this work as the workshop paper, so it was it's to be published. Okay. But yeah, that's. But you mean the comparison in terms of?
No. In general, the solution with you have worked on an edge computing solution, as you explained, and with one specific set of characteristics. But there are other edge computing solutions out there that people worked on, and they have different characteristics. I would be curious on how they compare to each other.
Yeah, so before writing the paper, we were looking for systems that have the same characteristic. We didn't find any. Okay. But yeah, then maybe broaden the scope of comparison.
Like the other solutions don't have blockchain. That may or may not be a good thing.
Sure.
I have my own opinion about that, but they have other interesting characteristics that your solution may not have. So maybe if you do that comparison, I would be drop a mail to the list. I would be interested to read that.
Thank you. So I have one more slide just to have some open questions that we still have. So if we assume that we have this network and we see it as a global computer, we would probably need something more efficient to dispatch tasks, because now it's kind of up to the nodes to negotiate the price and stuff like that. However, if you want to have a module that will just dispatch tasks automatically between nodes, then I think it's pretty difficult, because then if the payment is involved, how do we define fairness in this case? Especially if we have different prices, loads, and node capacities. Also, how to estimate the cost of the computations in terms of CPU, bandwidth, memory, quality of service, knowing again that we have very heterogeneous environment. and how to provide full privacy, because in this case, we protect input and the result, however, we still know who invoked which function. So this is also probably good to hide it as well. So I think that's all. Thank you. More questions? Okay. Thank you.
Thank you. So I think this was interesting also for people who thought that TLS was complicated, and I think we're going to see some really interesting security constructions to make things work in an environment where we can trust less. This, I think, is just an interesting example for that. And when you want to decentralize, you, of course, no longer always know who you are talking with. The last item on the agenda is a quick peek at the meeting schedule. Now I have to find my slides again.
They requested 2 minutes on that.
Yes. Why does that not work? Oops. Hey Dave, do you want to come to the mic?
Dave Taylor. So mine is not about the agenda per se, mine is about the logistics of getting there. The meeting is tomorrow afternoon in Prague, and I know several people are on the 7:20 a.m. flight out of Heathrow, so my question is, as far as carpooling, since this is before like Heathrow Express runs and so on, I'm organizing a car. Can I get a count of how many people would want to travel together? We would be leaving the hotel lobby at about 4:20 a.m. tomorrow. Okay. If you'd like to carpool and come together in a shared car, please raise your hand so I can count. 1, 2, 3. Anybody else here? Okay, I just need to give the concierge a count for how big of a car to get. So far I see 3 in this room. If you know of anybody else, let me know, because after this meeting, I will go and get the car booked.
So is anybody going via Stansted? Okay, good. So
Chris, just a short comment. I think the first Heathrow Express leaves at 5:10, but there's the Heathrow Connect, which actually leaves earlier. So, but I guess it depends on when you want to be at the airports.
Yeah, the concierge recommended for travel to Prague that you be at the airport like 2 hours in advance, and it's a 1-hour trip. So that's why he recommended 4:20 for car departure, or 7:10 and 4:10 for the car departure. So yeah.
okay. What we wanted to do is give you just a quick peek into the kind of things that we are doing at these coordination meetings. So this is the first time that we actually, no, it's not actually not the first time. It's another time that we're actually having W3C and OCF in one room together with a research group. And of course, we're going to do status updates between each other. We will also talk about Wishy again. But there are a few issues that really aren't standardized yet. And so, for instance, one issue that comes up repeatedly is that when you actually request some action from an IoT device, how do you know what data you actually need to send with that action so that the IoT device can do the right thing? So this is a slightly different problem from simply requesting data. You can request those data and then think about them and so on. But if you actually want the light to be green or the loudspeaker to be loud or something like that, how do you actually specify this in a way that allows interoperability? So that's one thing we're going to talk about. More generally, we will talk about model interoperability, so things we tested in the hackathon. Yeah, what's the next step to make sure the various models that are popular right now interoperate? The IPSO or lightweight M2M model is relatively simple and straightforward, pretty easy to translate. Thing description is very powerful. OCF has this RAML Swagger-based modeling scheme. So how do you put these things together? Another thing, again, on the protocol level is how do we model the various forms of pushing data. So we know publish, subscribe is a pretty popular way to model that, but also has its problems. And it would be interesting to see whether additional extensions of REST beyond what we already have in CoAP, which is the observe function, would be useful to better handle these push models. So there's actually a research group draft called Non-Traditional Responses, and we want to discuss how useful that would be. We want to talk about the area of data that you actually install or obtain from an IoT device about its relationships to other devices. So how can you actually bind a light switch to a light? How do you describe the interfaces? How do you build the links, and how do the resource representations look like? And then, of course, we have housekeeping on the base CoAP document, like new response codes, talking about the resource directory. There are different ideas on how to use that and so on. And finally, we are going to talk about ACE, the security, the authorization working group within the IETF, and how that could be useful for the OCF, which have their own security model already in place. And they also have interesting authorization formats and so on that we could talk about. But one interesting question is, how do we get multi-point security in? So somebody sent me a link to the Fair Hair white paper, the Fair Hair security white paper, which nicely describes how they are going to do all their security. And then there's this section 7, which hand waves about multi-point security. I think that's really something that we need to do somehow work on. So this is sustainabilization, and finally, of course, we all benefit from the availability of reference implementations and from test cases. So we want to discuss how we get a better situation with CoAP, particular CoAP over TCP, CBOR, and other standards that we are using. So this entire thing we want to do in one afternoon. That will be a rather cramped program, but yeah, we can always factor out things to telephone calls later on. So this is our next meeting. I already said a little bit about other meetings going on. And I'm pretty certain we are going to have a summary meeting at the Montreal IETF. So if you don't follow this working very closely, you can still come to the summary meeting and find out what we have been doing. So thank you for coming, and have a nice rest of an IETF.
Thank you. And if you haven't yet signed the blue sheet, please sign them before you leave. Thanks.
Oh ja.
Im Prinzip lief recht gut. Mehr oder weniger was rauskam, war die